Okay, so I will first give a little bit of an intro to pointers, structs, and then what I would like to do is quickly go over some of the SPI communication that you need to use, because you are going to a CAN laboratory, and a CAN laboratory actually requires you to communicate through SPI with the controller, and that will become much more clear later on. So in the end, what you will need to do is you will need to use a library for SPI. You have done that before already in the previous course, but we'll go over that again. But now let's talk about pointers. So let's just look at this little bit of code, because I think that's really the easiest to think about pointers. So first of all, if you think about a value, it's stored at some address, right? In storage, whatever the storage is. It could be DRAM, it could be something else, SRAM. Now, that particular address contains some value. Now, we see here two declarations. One says, well, I want to declare a variable var as an integer, and in this line, at the same time, we give it also an initial value. You see, you can do that. So you do first declaration, and then you actually initialize it to the value 1. So this variable, you don't see it, you do not know, but abstractly, this name var is now representing this value 1. But it must be stored somewhere. There must be an address associated to that. And the address associated to that you can find out by adding this, how do you call it? Like this and symbol.
Ampersand.
Right.
Ampersand. Ampersand.
Ampersand?
Yeah.
Okay. Ampersand. So you put it right before the variable, and that will be the address. Now, this particular line tells you that I would like to declare a variable that I call ADR of address, but I declare a pointer to an integer. So what is a pointer to an integer? It's to an integer value. It's actually a pointer. It actually represents an address where an integer is stored. So if you look at these three lines, and now we do the following print statements, well, if I want to know the address of where this variable is being stored, I can look, I can actually use this ampersand symbol before the var, and that will tell me, for example, this address over here, so some kind of address. And if I do the address stored in address, which is just a variable now, it's a variable, it does not have this ampersand in front of it, it's just a variable. And that variable was declared, was initialized by the address of where this variable was stored. So it will have the exact same value. Now, if I'm going to look at the value of what address is pointing at, right? Then I need to look. Then I will write it out like this. I have this star symbol in front of address, and that means that the address is being looked up in memory. Then you will have a look at what value is stored there, and that is being returned. Well, what is stored at this address? Well, it is the actual value 1. So that is what we do with pointers. So that's the pointer structure. Now, if we have an array, for example, then an array itself, like say an array that is called A, should have brought some markers, but I didn't. So if an array A, and say it has 100 elements, so declare this 100 elements, then A, just using the word A itself, is an address actually. And an address, if I look at the 0th position, then I'm interested in the value of what is stored in that address. If I look at A and then 1, for example, then I'm interested in the value that is stored at not the address, but the next address, address plus 1, if you will, and so on. So this is, so that kind of stuff you will not really see, but arrays are also defined in terms of pointer structures in a sense. And so let's have a look at this piece of code over here. So you may want to modify the content of some address, right? So say here we have two declarations, both n and x are integer values that are declared, initialized to 1 to 10 for n. And here again I have a pointer, which is simply again, with a star, it means I'm declaring pointer as being an address. That if I'm going to look at the value at that address, it should return an integer. So now say I again declare or I initialize pointer to be the address of this integer n. And then I can also assign to x, because it's an integer, the value that I see at the address of pointer by using this star. So what do we do here? We effectively know that if a certain address contains an integer, I can also access that value through the pointer. And I can use that in all kinds of instructions. So I can just actually have another y that can also make equal to that value that the pointer is pointing at. Now this is really all that you need to know right now. But what the plan is that actually I'm thinking about using this and actually the Wednesday lecture to go more through the Ken lab itself, and it will also show you, but that's not in the directories, but I'd like to show you some of the C coding solutions that we have, where we use these types of structures so that you can see how that works, and then you can also understand how, like, say you write a library, for example, what would you put in a .h file and what do you put in a .c file, right? And so forth. But we'll take it step by step. Now, there will be a first lab that is not at all part of any grading or what, but it is a very first setup lab with a bunch of test codes that you want to run just to see if everything works for you. But there's one little assignment that talks about pointers and structs for you if you like to experiment with. But once all your material is in good shape, then of course you would like to go ahead with the Canon lab right away. Now let's talk about structures. Yes?
So I noticed in the other slide that the address was 32 bits. So is it typically 32 bits?
It depends on where you run this at. Okay. So if you run it on your laptop, I would say yes. But if you're running it on an MCU, then obviously we have a much smaller amount of storage. You don't even know exactly how much it is. It is much smaller.
And then I was going to ask how the address, like how you know where it starts.
So it returns to start.
Yeah, you could use the star.
Well, no, like say you do like int n equals 10.
Mm-hmm.
And if how do you know what the address is like going to start? Like, why is it starting at that value of the operating system?
Oh, that is what the compiler and the operating system are doing.
Just that next available address.
Right. That's the beautiful thing about operating systems, because operating systems do all the resource scheduling. So they do the scheduling of all your memory, they do the scheduling of all your computing resources. So if you have multiple threads running, like on your laptop, you have, your interface, your different programs running, and the human is kind of slow, so you don't really see that it's really a sequential way of executing everything, but the operating system is in charge. And that's, at the end of this particular course, we also have a real-time operating system laboratory. And real-time operating systems obviously play a role in the robots, or as you don't have to use it for a final project, but it's good to know about it, because for general controls systems and so forth, you would like to have a real-time operating system. So we talk about FreeRTOS, and we would like to do that. You have a question?
Yeah, I was going to ask, so instead of storing a number at a variable, could you then store it at a specified address? Would you pick the address you want to store it at?
You could do that too. Yeah, absolutely. Yeah, you can just, like for example, this pointer. is initialized with the value of this address, but I could create my own address, but I have to be careful, of course. I need to know whether that address is not being used by something else. That's the reason why in C you would like to not directly allocate addresses or ranges of addresses, but you may want to tell the operating system that you want to allocate a, say, consecutive range of addresses for a certain data structure. And we'll come to that also probably on Wednesday when we talk more about the CAN laboratory itself, because you can then do what we do, a memory allocation to a variable that expresses that you would like to reserve a bunch of addresses. You don't care where it starts, but you care usually about the fact that there are next to one another. So, yeah, but so structures are really great to use. So what we will be doing, you can choose your own solutions, right? But what we have been doing in our own solution for this CAN laboratory is that we create a structure of a message. And the message will have, say, some data. It will have a message identifier. It will have maybe other components that all together will allow you to, you do not want to create separate variables for each message because that will be really cumbersome to understand, to read. Your own code will get messy. So why not create a type, like an integer type? Are you ready? Happy to see it. And so an integer type, or like an integer type, some other kinds of type, like that we call books. So we create a structure that is called books. And we say, well, if you declare a variable, book, right, according to this type, then we know that book has a field called title, author, and illustrator. So I will give you an example when we get to that for the message that you're going to transmit between over the CAN communication channel. But the point is that you can access this title by a few ways. You can do book.title, and then you get the title out of that variable book, or you can put an arrow title, and then you also get the title, and so forth. So this structure is really nice to use to make your code readable and easily manipulatable. Take, for example, you will be creating procedures for transmitting a message. It's much nicer to have a procedure that takes one argument, which is the message, rather than message identifier, data, and so forth. You have no clue anymore what all belongs to the message. And finally, you also have another field that says address, for example. But that address was not part of the message, but how do you know as a reader what is part of what? So this struct allows you to modularize units of information. And I think that's very important. So I hope you will adapt to that. Alright, so we will do the actual intro of this class later, because we have the lab, after this. And so we'll skip this particular slide for now, because I want to go over the very quickly go over this. Actually, I forgot to bring my pointer, but you have already studied SPI, and you will need SPI to communicate with the CAN controller. So, just I want to remind you that we have a clock signal that you need to have set between master and slave. You have a master output slave in, master input slave out, and you have a select channel, like which device you actually select. Now, in our case, you will have the MCU, and next to it you have the CAN controller. So, there's just one select, of course, that you will do, but those four channels are connecting the two devices. So that's what we will see when we look at the layout of what you need to put together in the hardware. So, there's a bunch of SPI data modes and so forth. I'm not going to go into detail with this because this is all hidden in the SPI code that you've already written. You can look that up in your own in your own files. So I do like to quickly go over this code because effectively what you're going to start out with in the CAN laboratory is to write an SPI library. Now you probably will copy over the SPI library that you had before, but we have changed it a tiny bit because that's what we did. You may not choose to do so, but the point is that if you're going to make some changes, then you need to have these components part of it. So for example, you need to initialize the SPI, right? So you will want to write an initialized SPI functionality that is going to set all these channels. And obviously, you would like to use names that make sense. And those names are depending on which ports and which pins you're going to use for those channels, right? For those 4 wires. And that you will have defined separately as a definition, right? So define, for example, DD_SS is equal to some PV something, whatever you choose. Now, so you will set this up. You will also do all of this stuff, and what would be probably a good thing to do is that you want to create. You would also want to initialize the pins. The right pins as output and the right pins as input, so that you make sure that it's all initialized in one go. So that we did not do in the code that you have from the basic course, right? But it will be good to add it in. But effectively the code is exactly the same. You do a transmission, for example, then you do exactly what we have done here. You do those, and that's it. So yeah, so that's what you would like to do. So look that up again, but that is what we will use in order to communicate with the CAN controller. And here we have the slave. It's pretty much the same type of code in a sense. Again, you want to initialize a bunch of stuff, and then you have the slave receive, where you simply wait till you can read this particular register. So that's it. So that's what this was about. But we have to look back into it again, and I like to stress that now that you're going to work with this again, don't forget the traps that you may have gotten in before, which is that if you program in ISP mode, right, you will need to restart Atmos Studio every time you program this process, this MCU. So better is to use debug wire, and then of course remember the debug wire interface requires this fuse to be enabled. But if you do so, you will have to before you go on, you need to. So where was this? But yeah, you will need to enable the DWAN fuse, and after that you need to actually disable it. So make sure that if you want to program your MCU again with other stuff. So remember to read this again. So that I want to quickly go over. Look at this slide deck again. It's always good to look at what kind of debugging you can do, because you will use that, and you can recap that at some point as well. So now I would like to go to the CAN laboratory, and I would first need to explain to you a little bit about CAN itself, obviously. So, alright, so first of all, take for example a car, and you will notice, I don't know what is the sharp here, the sharp, you will notice that there are 2 types of communication protocols, CAN and LIN. LIN is a simplified version of CAN, and it's a very cheap communication mechanism, and you will find it in all kinds of, especially in a car, in all kinds of systems. And what does it do? Well, CAN is based on message-oriented broadcasting, And you will actually, what you'll see is you will have two wires for communication that help, that are designed in such a way that you can reduce internal noise a lot. Message is identified by a message identifier, which is great. And you know, the message identifier defines not only the content but also the priority. The lower the message identifier, like the closer it is to 0, that means that that message will have the highest priority, because I will explain in a moment how arbitration happens. How do you know which peripheral needs to pick up on that message, or which message is going to be transmitted at that particular moment in time? Well, it's the one with the lowest address, and that was the highest priority. Now, it's great for short-range communication and so forth. So this is very quickly, but let me explain a little bit more about the two frame formats. You have a standard one and an extended one, and it's simply the number of bits that are used to identify a message. There are a bunch of frame types, like a data frame, there's an error frame, overflow, overload, remote frame. But what's the structure?